Good morning. I would like to first thank all of the organizers, Eriki and Hoyos and Victor. And in order to do this so hard work, I also have the help of many people. Oh, is it working? Yes. I have the help of many people, so I have to also to thank my collaborators, so all of them here, Bo Xiao, Sankatami, George Baltruni, and Richard Scolator. So there is another pointer. And also all of the financial support given by these funding agencies. So I divide my presentation this way, where I first will present some introduction about the, okay, great. Some introduction about the superconductivity and charge density wave, in particular, using the background of transition method, Inhomogeneities. And then I will introduce you the Holstein model, no, not Hubbard, Holstein model. And then I will give you some results, my conclusions, and outlooks. So that's fine. So when we talk about the electron-phonon interactions, actually this is one coupling that leads to two different phenomena. It leads to superconductivity, these things we know from Bargin, Cooper, and Schrieffer, and also leads to charge modulation. The second one was a phenomena that was explained by Pyers long time ago that basically give us this, the simple explanation that if you have nesting at your Fermi surface, and if you have one electronic instability like electron-phonon coupling, you leads to a charge gap here in your single particle spectra, and also you lead to a phonon softening in the cone anomaly in a vector equal to 2 times the Fermi momentum, and also you have a Lattice distortion, a permanent Lattice distortion. This is what Pyers gave us as a result of the one perturbation theory for electron-phonon coupling. And this really happens in nature. For instance, this is one example of quasi-one-dimensional organic material that exhibits this kind of Pyers-like behavior. But this is not true for all materials. If for instance, if you discuss the transition method, the Chalcogeneities, for instance, here I will focus on this niobium desalinate. It doesn't have any of these features, any of these ingredients that leads to Pyers instability, even though it has charge density wave. So studying the nature of the charge density wave is something that's very, very interesting because there's many other roads beyond the Pyers instability. But this was my talk 5 years ago, so I have to move on. This is what this was the main issue of my talk 5 years ago in the same workshop. So now what I will do is basically in this new workshop, I will discuss the interplay between superconductivity and charge density wave. And when we are discussing the interplay between these two phenomena, it can come from many different experiments. For instance, we can have it by doing gate-induced experiments, but also you can do this by applying pressure. And also you can have it by doing disorder. And here, this is one example. And this is the main issue of my talk. I will give you some insights about what happens in this case here. So, okay, so by performing disorder, we can do this by applying, for instance, intercalation. So we have in this transition method, Chalcogeneities have weakly coupled layers, and you can put, for instance, atoms here in this space between layers. When you do this, for instance, for niobium desalinate, one main characteristic is that you have a broadening of your X-ray intensity peak, and this broadening basically means that you are losing coherence. You are losing it's not coherence, but losing your correlation length is becoming less. Is diminishing, and you also have a reduction of your critical temperature for charge density wave. And how can we understand this? Basically, you can understand this by looking the order parameter. The order parameter of charge density wave is basically the fluctuations of the charge density. And if you are putting atoms inside this space between layers, you are basically doping the layers with electrons, and these electrons can change locally the phase of your order parameter. So this is quite similar what happens in superconductivity, because here now we have, for instance, a random field similar to what Thomas had discussed with us on Monday, that destroys the coherence of your pair. So you still have electron hole pairs, but you don't have any more coherence between them, because this random field destroys it. So this is ARP's measurement that shows that your peak away from the Fermi level is destroyed. So you still have a gap, but you don't have coherence between your electron hole pair. Actually, what you have is basically, if you perform STM, you have these puddles of strong correlated charge density wave, but with a lot of domain walls. Another way to do disorder also is performing the chalcogen substitution. If you do this, for instance, changing selenium by sulfur. Yes. Oh, yes, yes. So what happens here is your temperature is pushing down with disorder. And for a concentration like 1%, you already destroyed the charge density wave. This is enough to destroy the charge density wave. So it's a very small disorder is enough. On the other hand, you can do disorder by applying, by substituting, by doing isoelectronic substitution, change selenium by sulfur. And here, for instance, if you look for the properties of selenium and sulfur, you see that they are very similar, but changes a little bit with concerning to the atomic mass. So basically, what happens is you do not change you do not dope with electrons, but you change the coupling with the chalcogen, with the transition metal, with the transition metal, and also you change you locally change the electron phonon coupling. So this is what on Monday we learned from Thomas, that this is called as the TC disorder. Right? So you should expect that nothing should change, but just some field changes should occur with the temperature, with the critical temperature. But actually what happens is this. Since we have two phenomena coming from the same coupling, we cannot preview what happens. And basically what happens is you destroy charge density wave and you have the enhancement of superconductivity. So because the same coupling leads to these two phenomena that compete with each other. So what I will do is focus my attention on this case by doing something that's much more simple than the complex materials. So what I will do is I will work with a square lattice that I have atoms here, and then I will allow the atoms to shake. So I have quantum harmonic oscillators in each side, and then I have electrons that can hop from one side to the other, and then I have this indirect interaction between electrons because I have phonons in my system. So I don't have Hubbard interaction. Okay, so just electron-phonon interaction. This is my Hamiltonian. But what I will do more is I will put an Anderson-like disorder here in this term, and I will look what happens with my long-range order. Okay, so since I'm interested in charge density wave and superconductivity and and things like that, I have to analyze the charge structure factor, the pair susceptibility, the conductivity, and things like that. But the thing that is more important here is that we have many parameters. We have temperature, we have the adiabaticity ratio, we have the electron phonocoupling, we have also let me see, there is one more. The filling. So we have to fix some of them, and then I will fix this two here. Is basically I will discuss them later. Okay, I will skip these details about the model just to save time to me. But basically, I would like to recall to you that in this case, we don't have sign problem. Okay, so let me go to the results. First of all, I have to remind you that for the squarelets, we have the half-filled squarelet has the Van Hoff singularity and also has nesting. So we have this Pyors instability. We have the ingredients for Pyors instability. And indeed, if you look for the charge structure factor, it increases a lot with the system size, what is a signature that we have charge density wave. And since these have the same the same universality class of the Eisen, we can also perform such kind of data collapse and obtain the critical temperature. So everything works here. And if you look here as well, we see that we have one metal insulator transition because we have a gap on the density states. We can see this gap for instance, by looking the compressibility, the behavior of the density as a function of the chemical potential. This is really important to me later. Okay, so let's move on and discuss what happens when we put Anderson-like disorder. So we learn. Yes, I have partial hole symmetry. So I have to remind you what to learn from Thomas on Monday, that if we have this kind of disorder here, this disorder couples linearly with the order parameter. So for in-Remar argument, we could not have long-range order. So I will not talk about long-range TW order here because we don't have long-range order. But we still have, just because of this domain walls, but like presented in this work, but we still have this short-range puddles. These puddles with short-range strong correlation. So this is what I mean for CDW here. Okay, so let me start discussing this strong coupling regime first. So in this strong coupling regime, again, looking for the the structure factor, the charge structure factor. When you put this order, you reduce the peak of the structure factor as a function of beta. Here is the inversion of the temperature. So you don't have more this very nice, very clear peak of the structure factor. So this is expected. But the first thing that you think here is that, okay, here you have destroyed this puddles, these CDW puddles, then you have a metallic state. But this is not what we see by the kinetic energy. Looking by the kinetic energy, you have an increase of the kinetic energy as a function of the inversion of the temperature, what is unusual. So to really analyze what happens in this case, we have looked to the DC conductivity, and we see that it goes to 0. So it means that we destroy this charge density wave, but we don't have here a metallic or a superconducting state. We have an insulator state. So this is a little bit unusual. Again, here we can show. I show you the pair susceptibility that goes to 0 as well. So we don't have superconductivity. So the first question to us is that, okay, we have we have a crossover from a short-range CDW insulator to another insulator that we don't know what the nature of this. Because I would expect that should be superconductivity since I destroy the CDW state. So in order to understand the nature of this insulator, we have to analyze two other quantities. First, the spectral weight. So here we see that we have really a gap in line with the previous results. But when we try to analyze the compressibility, the density as a function of the chemical potential, we have a completely contrasting result. Because here we have an insulator, but when you perform the density as a function of the chemical potential, it seems that it has it's gapless. But what happens here is basically that it's easier to the system to add 2 particles instead of 1 particle because you have a strong electron phonon coupling. So this is a single particle gap state, but it's 2 particle gapless. And this is one very different insulator. This is what we call as Bose insulator. So this is the first result that you got. Probably my time is over, but I will just finish quickly. If we go to the weak coupling regime, we have the completely different result. So when CDW goes to 0, you have a very clear peak in the pair susceptibility. And this peak here, if you look in this inset, we see that we have a long-range order, really. And we could also, I will skip the details behind this, but we could also show that this has the Costa-Listaulis universality class. And basically, the final result that we got for this weak coupling is that if we destroy superconductivity, destroy CDW, in this case here, you got charge dense wave. Oh, sorry. If you destroy charge dense wave, we have superconductivity here. So these are my conclusions. You have 2 different results here, depending on the strength of your coupling. If you are in the strong coupling regime, you can have this Bose insulator. But if you are in this weak coupling regime, you can have the superconductivity in emerging. And as my conclusions, as my outlooks, everything can change if you put a Hubbard-like term, and everything can change if you put off-diagonal disorder. This is TC disorder, but this one I don't have time, but my students are doing. So that's it. Thank you very much.
Thank you, Natanael, for this nice talk. So, first question.
So if I understand you correctly, in the strong coupling limit, you actually form some kind of a bipolaron, right? These 2 carrier, they bind together locally, and that's why you have a gap in the
yes, exactly.
So it's some kind of bipolaron, right?
Yes.
Okay.
Yes. The main point is that I have not time to discuss this, but if you are in the strong coupling regime, your polaron is small.
Right.
So disorder is very important because you can localize the electrons. But if you put 2, if you have a bipolar, right, it allows. Right.
And then the second question is that you show that the compressibility, there is no real. So you call this a Bose insulator.
Yes.
But because you have a gap in the 1 particle Green's function, is that right?
Yes.
But why is it? Because the binding of the bipolaron is not infinite. Why is it that they couldn't move together? You would have thought that there is a T² over binding energy, which is non-zero. So wouldn't that be some kind of
Yes,
Bose
this is
liquid?
a good question. This is a good question. But actually, let me show you this result. What we do here is we look for the conductivity, basically by doing current correlations, and this is 0. So I do not expect that pairs could.
No, because you're looking at the particle correlation function or current function of the fermion. Now, do the 4-particle Green's function, the boson particle correlation function or the current correlation function, you'll find it's non-zero.
Yes.
It's actually a metal. It's a Bose liquid.
I do not. Okay, great.
Natanael, I was just to confirm, I understand one thing. What is the CDW wave vector? It's incommensurate with the lattice?
No. All of these are. Oh, sorry. All of these results are for the pi. Let me show you.
But then I would expect that in this case, the random chemical potential will not be a random field anymore.
No. Everything here is in the half filling. So although you have although we have this disorder in the densities, we still have, in average, the pi being the peak. So the pi is the one that peaks. If you are away from half filling, maybe not. Maybe
Okay.
you change it.
So CDW can survive them? in
Yes,
the- okay,
yes.
okay.
No. Long-range order doesn't exist here. We have these puddles because in Grimoire, argument doesn't allow you to have long-range order. So because your disorder couples linearly with the order parameter. So what you have is you have these puddles with strong charge correlations that you can destroy it, and you have.
Okay.
So what I mean here by CDW is not long-range order. It's like what experimentalists call as incommensurate CDW and things like it.
Hi. Yeah, very interesting stuff. Did you ever? Is it possible to look at lambda xy, the current? You know, in the regime where you have this boson insulator-like phase at strong disorder, it would be quite interesting to know what the Hall response, if it could be measured in QMC, would be like.
Yes, it's possible to measure. We didn't do this, but
Okay, I think that should be very interesting.
okay, nice. Thank you.
A very nice talk, and actually, there is I think, a connection to what I was discussing yesterday, in the sense that, I mean, we were talking about spinless fermions, but I think in this case as well, this is not what this shows is that the compressibility being finite, is that this actually survives at any filling. That this is not a property, whatever you find, this amorphous state, which has some short-range order or not, it is not found only at half filling, but it's found at any filling.
Yes.
And the formation, so if you can imagine that I can crank up, say, the disorder and some moderate electron phonon coupling, then this charge density wave, if you're not at some special filling or nesting, there will not be a charge density wave a weak disorder, because it requires some nesting or special filling.
Yes.
But if you crank up the electron phonon interaction, this formation of these polarons, which will get stuck, that will happen at any filling, and it will open a gap in all sectors. I think that answers a question away. In absence of disorder, these bipolarons, they can move, and they can rearrange. But in presence of disorder, they can actually kind of get stuck, and they are actually interacting with each other as well. I mean, he didn't put this, but there are Coulomb interactions, for example. And so they will form an amorphous solid, which is an insulator. But that's an insulator is very different from an Anderson insulator.
Yes,
Right?
exactly.
So can you actually study the situation first gapless, spinless, B, or even if you have spin, just start with weaker electron phonon interaction at arbitrary filling, and then just crank up the disorder. And is there a metal insulator transition?
Yes, it's doable,
So
because here we
has
don't have sign problems. So,
this has not been done.
Okay, good.
Because
Good.
it's
So
a very
will-
different
I will take
flavor,
notes.
but I think it's really connected to this, right?
Okay, great. I will take notes on this.
So I guess we have to call it a day. So thanks, Natanael. Let's thank all the speakers
much.
again. And then we meet again